13.4 billion years ago, light began a journey that would end in our telescopes. It came from something that should not exist. In that distant corner of the cosmos, a tiny galaxy blazes with the brilliance of a mature system, but it was born when the universe was still a baby. At that time, space was dark, quiet, and empty. No heavy elements, no long-lived stars. Just hydrogen and helium drifting in a young and fragile cosmos. And yet this small galaxy shines as if it had lived for billions of years. It contains oxygen, an element that takes multiple generations of stars to forge. But those generations shouldn't have had time to be born, burn, and die. This is not just another distant dot in the sky. It's a crack in our understanding of cosmic history. If the laws of the universe are correct, this galaxy shouldn't be here. And yet it is. The light we see from this galaxy is ancient. It left its source when the universe was just 2% of its current age. Every photon carries a message from an era when no galaxies like this were supposed to exist. Back then, space was still wrapped in the aftermath of creation. Gravity was only beginning to gather clouds of hydrogen and helium. Stars were rare, young, and short-lived. Galaxies, the great cities of stars, were only whispers in the dark. But when James Webb's Space Telescope looked deeper than ever before, it found something impossible. A galaxy so bright, so chemically complex, that it felt like peering billions of years ahead of schedule. Its light has travelled across the expanding fabric of space for longer than our planet has existed. The very atoms that make up that light were forged in stellar furnaces older than Earth's crust, older than the sun itself. This is not just an ancient object. It's a snapshot of a universe that shouldn't look like this, not yet. What makes this galaxy impossible is not its distance, but its chemistry. Oxygen is a latecomer to the universe. It does not appear in the fireball of the beginning. It is minted inside massive stars as they race through their short, furious lives, then thrown into space when these stars explode. Only after this ash cools can new stars be born from it. That cycle must repeat again and again before oxygen becomes common. But the snapshot we are seeing was taken when the cosmos was only a few 100 million years old. That is barely enough time for gravity to gather clouds, ignite giants, and let them die, let alone to repeat the process. Yet the spectrum of this tiny system carries the unmistakable signature of oxygen, as if several stellar generations had already come and gone. Either the first stars formed earlier than we thought, or they were far more massive and efficient at seeding space than our models allow. Both paths bend the timeline. Both threaten the story we tell about cosmic dawn. So which failed us, our clock, our physics, or our expectations? Imagine compressing the entire history of the universe into a single year. In that cosmic calendar, the Big Bang happens at midnight on January 1st. The formation of our galaxy comes in late summer. Earth appears in September. Humans arrive only in the final minutes of December 31. This tiny galaxy, it shows up on January 7th. That's how early it existed before the cosmic stage was even built. At that point, there shouldn't have been enough time for stars to live, die, and fill space with complex elements. Seeing oxygen in its spectrum is like finding a library in a town that hasn't even poured its foundation. Something in the early universe moved much faster than we thought, or something in our story is missing. And that gap is not small. It reaches across hundreds of millions of years straight into the foundations of cosmology. We once believed the early universe was simple, a quiet expanse of hydrogen and helium waiting patiently for gravity to sculpt the first stars. In that story, galaxies emerged slowly like ripples spreading across a calm lake. But this galaxy doesn't fit that picture. It burned bright when it should have been nothing more than a faint seed of light. Its presence forces a question that cuts deep. Are we seeing an exception or the true nature of the young cosmos? If this is not a cosmic accident, then the timeline of star birth and chemical enrichment is wrong. Maybe galaxies bloomed faster. Maybe stars lived shorter, fiercer lives. Maybe the universe itself was built for speed in those first moments. Either way, something fundamental has been hiding in plain sight, written into the light of a tiny galaxy at the edge of time. To understand why this discovery is so unsettling, we have to return to the very beginning. In the first instant after Big Bang, the universe was nothing like the star-filled sky we know. It was a furious storm of energy expanding faster than anything we can imagine. Temperatures soared to billions of degrees. Matter did not yet exist as atoms, only a dense, glowing plasma of fundamental particles colliding in chaos. In this newborn cosmos, light could not travel freely. Photons scattered off free electrons like headlights in a blizzard. The universe was bright but opaque, brilliant but hidden from its own reflection. No galaxies, no stars, no structure, just a storm slowly cooling. This is the stage on which the first chapter of cosmic history was written, and it is from this chaos that everything, including that impossible little galaxy, would eventually emerge. As the universe expanded, its furious heat began to fade. Particles slowed and the wild plasma started to settle. Within the first 3 minutes, protons and neutrons locked together, forging the simplest atomic nuclei. This brief era, Big Bang nucleosynthesis, created almost everything the cosmos had to work with for hundreds of millions of years. Hydrogen dominated. Helium came next. Trace amounts of lithium flickered into existence. But that was all. No carbon, no oxygen, no iron. The cosmic ingredients for stars, planets, and life did not yet exist. The early universe was a blank canvas with only 2 colors: hydrogen and helium. Everything else, every heavier element in your body and planets in stars, had to be forged later, inside stellar furnaces that had not yet been born. For the next hundreds of thousands of years, the universe continued to stretch and cool. Electrons finally slowed enough to be captured by atomic nuclei. In that instant, the fog lifted. Photons broke free and began to travel unhindered, filling space with a faint afterglow that still lingers today, the cosmic microwave background. The cosmos became transparent for the first time, but it was also dark. No stars shone yet. No galaxies had formed. There were only vast clouds of hydrogen and helium drifting in silence, shaped only by the invisible pull of dark matter. This quiet epoch would last for hundreds of millions of years. Astronomers call it the Cosmic Dark Ages, a time before structure, before light, before the first sparks of creation lit up the void. Then in that darkness, the universe was not uniform. Tiny fluctuations, ripples left over from quantum noise in the first moments after the Big Bang made some regions slightly denser than others. These invisible wrinkles were the seeds of everything to come. Gravity went to work. Denser regions pulled in more gas, growing heavier and more compact with time. The cosmic web began to take shape long before a single star lit the night. Hydrogen and helium slowly drifted toward these invisible wells, following the silent scaffolding of dark matter. Nothing burned yet, but in these quiet convergences, the first galaxies were already being written into the fabric of space. The universe was laying the foundation for its future light. In the silence of the cosmic dark, gravity began to whisper. Those invisible wells in the fabric of space deepened as gas drifted inward. Hydrogen and helium, the only ingredients in existence, responded to that pull like water flowing down a slope. Over millions of years, vast clouds gathered around these gravitational basins, slowly growing denser and heavier. As density increased, something fundamental shifted. The temperature at the heart of these clouds began to rise. Pressure built layer by layer like a hand closing around a beating pulse. For most of the cosmos, nothing could be seen. But deep inside these forming clouds, the stage was being set for the first fire. This collapse was not fast by our standards, yet for the universe it was stunningly quick. In less than 200 million years, the Dark Ages would end. The physics is simple but relentless. As gas compresses under gravity, it heats up. As it heats, it loses energy through radiation, allowing it to compress even further. This feedback drives the core to higher and higher densities. Eventually, the heart of these clouds reached tens of millions of degrees. The building pressure was unstoppable. Nature had created the perfect furnace without metal dust or planets. only hydrogen, helium, and time. The edges of the cloud continued to fall inward, feeding the core. For the first time since the Big Bang, the universe was preparing to ignite light not born in a flash of creation, but in the slow, patient burn of stars. And when that first spark of fusion finally erupted, the darkness that had lasted for hundreds of millions of years would be gone forever. A single ignition in a silent void would signal the beginning of everything else. Then in the depths of those collapsing clouds, the first stars were born. They were nothing like the stars we know today. Without metals to cool their birthplaces, they grew far more massive, some tens, some hundreds of times the mass of our sun. These were cosmic titans, bright, violent, and short-lived. They burned their fuel with an intensity that left no room for moderation. Their light was piercing, flooding the surrounding gas and tearing electrons away from atoms. For the first time, darkness met resistance. These stars carved glowing bubbles into the night, ionizing the hydrogen around them and reshaping their environment. What had been a silent fog became a luminous, turbulent sea. Inside their cores, fusion worked with brutal efficiency. Hydrogen fused into helium into heavier elements like carbon and oxygen, but only near the end of their brief lives. These first stars didn't shine for billions of years like our sun. Many survived only a few million years before their cores collapsed under their own weight. Their deaths were no less spectacular. Supernova explosions ripped through the void, scattering the first heavy elements into space. This was the beginning of cosmic enrichment, the moment the universe started to manufacture the ingredients for everything that would follow. Galaxies, planets, water, and eventually life. With their birth, the long night was over. The era of darkness gave way to the era of light, and the universe began to build. The birth of those first stars triggered a chain reaction across the young cosmos. One by one, pockets of gas collapsed and ignited, each new light adding its glow to the dark canvas. These stars were scattered like sparks across an ocean of night, isolated yet connected through gravity's invisible web. Their combined radiation began to transform the universe itself. The intense ultraviolet light they emitted tore electrons from surrounding atoms, creating vast ionized regions that expanded outward. This marked the dawn of cosmic reionization, a slow but unstoppable process that turned the fog of neutral gas into a transparent cosmic sea. For the first time, starlight could travel great distances without being smothered. The young universe began to glow softly, no longer hidden beneath its own veil. Galaxies as we understand them did not yet exist, but the scaffolding was already in place. These early stellar clusters, small, fragile, and short-lived, were the blueprints for the grand spiral cities of stars to come. In this quiet but transformative era, the universe learned to shine. The cosmic night was fading, and the first outlines of structure were beginning to appear against the darkness. As reionization spread, the universe grew more transparent and dynamic. Regions filled with newborn stars clustered together under the pull of gravity, merging and assembling into larger structures. These stellar nurseries were unstable, chaotic places where new stars were born, lived fast, and died young. Explosions were common. Radiation was intense. The early cosmos was not a peaceful dawn, but a storm of creation. In this turbulent era, gas was constantly being pulled inward and blown outward. Supernova blasts carved cavities into surrounding clouds, pushing gas into new shapes. Those shock waves acted like sculptors, triggering fresh waves of star formation in nearby regions. What began as scattered points of light was now starting to organize into the first proto-galaxies, the rough blueprints of the galactic giants that would one day dominate the cosmos. Each one was small by modern standards, but their role was immense. They gathered mass-seeded heavy elements and created the first gravitational hubs. The young universe had finally built the foundation it needed for galaxies to flourish. The first galaxies were fragile things, small islands of light adrift in a vast ocean of darkness. They were nothing like the grand spirals or giant ellipticals we see today. Instead, they were dense, clumpy structures filled with hot young stars and turbulent gas held together by gravity. that was only just strong enough to resist being torn apart. Their lives were short and violent. A single powerful supernova could disrupt entire regions, blowing away star-forming gas and slowing further growth. But these same explosions also seeded the surrounding space with the first heavy elements. Bit by bit, the raw hydrogen and helium were laced with carbon, oxygen, and other building blocks of the modern universe. Every generation of stars left behind more of this stellar ash. Over millions of years, the universe began to enrich itself, turning from a simple chemical soup into something more complex. These fragile galaxies were not just glowing ornaments scattered through the void. They were cosmic factories tirelessly shaping the ingredients of the future. In time, these early galaxies began to cluster together, pulled by gravity, into larger and more complex structures. Streams of gas flowed along the filaments of the cosmic web, feeding their growth. As they merged and collided, their stars and gas clouds were thrown into violent dances, compressing and sparking fresh rounds of star formation. The universe was no longer just lighting up, it was building momentum. The cycle was relentless. More stars meant more supernovae. More supernovae meant more metals, the heavy elements forged in stellar cores. With each new burst of enrichment, cooling became more efficient, allowing gas to collapse even faster into new generations of stars. This feedback loop accelerated the pace of cosmic construction, and all of it was happening astonishingly early. Barely a few 100 million years after the Big Bang, the blueprints for modern galaxies were already being drawn. The cosmos was young, but it was not slow. It was moving with a speed that would one day lead to something extraordinary and something puzzling. To understand why the discovery of that tiny galaxy is so unsettling, we must look closely at the clock of cosmic history. Heavy elements like oxygen, carbon, and iron do not appear instantly. They are forged deep inside massive stars and released only in their explosive deaths. The timeline is built on the lives of stars, and stars, even the fastest burning ones, need time. First, hydrogen and helium collapse into the earliest generation of stars. Those giants live a few million years at most before exploding as supernovae, scattering their newly forged elements into space. The gas must then cool, mix, and collapse again to form the next generation of stars. Each cycle adds a little more complexity to the cosmos, but each cycle also takes millions of years. To build up the amount of oxygen seen in that early galaxy, several of these cycles would be needed. That means not just one generation, but many happening in rapid succession. The math doesn't fit neatly. There simply shouldn't have been enough time for the universe to climb that chemical ladder so quickly. And yet the light from this galaxy carries the unmistakable fingerprint of oxygen, a chemical signature that tells a story older than the timeline allows. Massive stars may live fast, but even they cannot rewrite the laws of time. A single stellar generation can produce oxygen quickly, but not in the quantities that astronomers observed in that galaxy. To reach such levels, multiple generations must have risen and fallen in a cosmic heartbeat. Think of the process like a relay race. One team of stars runs its brief blazing course, then hands the baton in the form of an enriched gas to the next. Each new generation starts with more metals, burns hotter, and adds more complexity. But that passing of the baton takes time. Stars must form, live, explode, and their ashes must spread. Simulations of the early universe show that even with the most extreme conditions, it takes at least several 100 million years to achieve the oxygen content measured in that galaxy. Yet the light we see from it was emitted less than 300 million years after the Big Bang. Something in that timeline is off. Either the stars formed far faster than we ever imagined, or the story of the early universe is missing a chapter. Astronomers have tried to bend the rules of their models to make the numbers fit. One idea is that the first stars were far more massive than expected. If nearly every early star was a giant burning through its fuel in just a few million years, then more oxygen could have been produced more quickly. A population of stellar titans could in theory enrich their surroundings in record time. But this explanation has problems. Massive stars are harder to form and require enormous amounts of gas. They live short lives, but they also explode violently, blowing material away from the very regions needed to create the next generation. Too many of them, and star formation could stall instead of accelerate. Another idea suggests that supernovae in the early universe were more efficient at spreading their metals through dense gas. The explosions might have enriched surrounding clouds faster than in later epochs. But even then, there's a hard limit on how quickly new stars can form after that enrichment. The chemistry moves fast, but not this fast. The more the models stretch to explain the timeline, the more fragile they become. Something deeper may be at play. Some researchers have proposed even more radical possibilities. What if the timeline isn't just stretched? What if it's wrong? Perhaps the conditions of the early universe allowed gas to collapse into stars far faster than our current physics predicts. Maybe cooling mechanisms we have yet to understand let those primordial clouds ignite with unprecedented speed. Others point to exotic scenarios. What if gravity behaved slightly differently under those early extreme conditions? A universe that forms stars more efficiently at high densities would leave fingerprints exactly like the ones we see in this galaxy. Even a tiny deviation from standard physics could change the cosmic clock dramatically. There's also the possibility that the first stars were not just massive, they were extraordinary. Titans hundreds or even thousands of times heavier than the Sun, burning like brief brilliant matches. Their violent lives could have flooded space with heavy elements, in record time rewriting the chemical timeline in a single generation. Each of these ideas is bold, none of them is proven, but they all point to the same unsettling truth. Something about the early universe doesn't add up. What makes this mystery so compelling is how clean the evidence is. The oxygen signature in the spectrum of this galaxy is not faint or ambiguous, it blazes clearly in the data. Astronomers can trace its wavelength with precision, measuring how much the light has stretched over billions of years. That shift places the galaxy at a time when the universe was still in its infancy, only a few 100 million years old. The strength of the oxygen line reveals more than just presence. It tells us how much of the element was there. And what the instruments found was not a trace amount but a concentration comparable to galaxies billions of years older. This is like finding an ancient child with the fingerprints of an adult. No single observation could carry this weight alone, but multiple instruments and teams confirmed it independently. The result stands firm. The galaxy exists, its oxygen is real, and the timeline, at least as we know it, is broken. The telescope that made this discovery possible is one of humanity's most extraordinary machines. The James Webb Space Telescope. Designed to peer deep into infrared light, it can look farther back in time than any instrument before it. When light travels across the expanding universe, it stretches like a rubber band, shifting from visible wavelengths into the infrared. Webb was built precisely to catch that stretched ancient glow. Its sensitivity is staggering. Cooled to near absolute zero, its detectors can pick up the faintest traces of galaxies born just a few 100 million years after the Big Bang. Webb doesn't just take pretty pictures, it dissects light, spreading it into spectra that reveal what elements are present, how hot they are and how fast they're moving. When Webb turned its gaze to a small, seemingly empty patch of sky, it caught the red light of a galaxy so distant it should have been invisible. But it wasn't. It was bright, structured, and chemically mature. This is the observation that cracked the timeline open. The light from this galaxy was so faint that even a small amount of interference could have buried it. But Webb's mirror, with its massive collecting area and extraordinary stability, captured it cleanly. Over long exposures, the galaxy revealed itself not as a blurry smudge, but as a clear red dot, its colour, a direct consequence of how much the universe had stretched its light. This redshift is a cosmic clock. The more space has expanded, the redder the light becomes. By measuring the wavelength precisely, astronomers can tell exactly how long the light has been travelling. In this case, the number was staggering. More than 13 billion years. That means the photons hitting Webb's detectors began their journey when the first galaxies were still forming, when cosmic dawn was only just beginning to break. But the spectrum carried more than just distance. It carried fingerprints, chemical signatures etched into light long before Earth even existed. When the light was broken down into its spectrum, a single feature stood out, a bright spike where oxygen speaks. Oxygen atoms, when heated and energized, emit light at very specific wavelengths. Over billions of years, that light was stretched and shifted, landing exactly where James Webb Space Telescope could see it. This was not a faint whisper buried in noise. It was a clear, sharp signal impossible to mistake. The oxygen line was strong, bright, and undeniable. At such an early time in the universe, seeing oxygen at all is extraordinary. Seeing this much of it is something else entirely. It was a fingerprint from a galaxy that had lived a story far more complex than its age should allow. The oxygen line is more than a marker, it's a cosmic timestamp. Its wavelength reveals how much the universe has stretched since those photons were born. From that single measurement, astronomers can rewind the clock, tracing the light back to a universe less than 300 million years old. At that age, no galaxy should be chemically mature enough to shine with such a signature. But the strength of the line tells an even more dramatic story. This isn't a faint trace hidden at the edge of detection. It's a bright, well-defined spike revealing not just the presence of oxygen, but its abundance. A young galaxy simply shouldn't have had enough stellar generations to create such enrichment. The instruments captured it cleanly. Independent teams verified it. The data stood firm. It was not a technical glitch, not a trick of noise, but a message from the dawn of structure itself. When astronomers confront evidence this strong, they look for cracks. Could the light be coming from something closer, masquerading as a distant object? Could the oxygen line be misidentified or shifted by some trick of the instruments? Every possibility was tested. None of them held. The redshift was measured precisely. The line matched oxygen at the expected wavelength, stretched by a factor consistent with the universe still in its infancy. Other spectral features lined up perfectly, painting a single clear picture. Even accounting for uncertainties, the galaxy's distance and composition were undeniable. This left only one conclusion. The galaxy was real, and it was far too chemically evolved for its age. A single observation could be doubted. A chain of confirmations could not. What Webb had uncovered wasn't an error. It was a challenge to the timeline itself. The oxygen signal wasn't just detected once. It was confirmed through independent checks, cross-reference with multiple instruments, and processed using different methods. This level of scrutiny matters because faint signals can easily be confused with background noise or statistical flukes. But this one remained rock solid. Each measurement aligned precisely with the expected wavelength for oxygen at that epoch. That meant astronomers weren't just seeing a red dot. They were identifying a specific element at a specific time with precision that leaves little room for doubt. Even the slightest error in wavelength would have shifted its position on the cosmic timeline, but the signal stayed where it belonged. This level of precision is what turns light into evidence. Tiny shifts in wavelength tell astronomers not only how far away something is, but how old the universe was when the light left. And in this case, the numbers didn't bend or blur, they locked in place. With the oxygen signal confirmed, the galaxy could no longer be dismissed as a statistical outlier. It wasn't a mistake. It wasn't a ghost in the data. It was a real object with real chemical complexity existing when galaxies weren't supposed to be this evolved. This is where the mystery sharpens. The physics works, the measurements work, but the timeline doesn't. When astronomers look this far into the past, precision becomes everything. A single misplaced wavelength can shift a galaxy by billions of years in cosmic history. That's why the instruments on James Webb Space Telescope are built to catch not just light, but the shape of that light. Every bump and dip in the spectrum encodes information about time, distance, and chemistry. For this galaxy, the pattern was clear and sharp. The oxygen line stood exactly where theory said it should be. if the light had travelled more than 13 billion years, not smeared, not distorted, perfectly aligned with an impossibly young epoch. Every spectral line acts like a thread, and when pulled carefully it reveals the structure of time itself. For this galaxy, those threads pointed to one place only: the early universe. No alternate interpretation could explain the alignment of the data. Astronomers know what noise looks like. They know the false signals, the glitches, the shaky edges of uncertain detections. This was none of those things. The oxygen line had shape, strength, and clarity. It sat in the spectrum like a signature on a document declaring its origin with confidence. The light had travelled across almost the entire age of the universe to deliver its message, and it was heard. When photons travel for more than 13 billion years, even the tiniest error matters. A shift of just a fraction of a nanometer can change a galaxy's place on the cosmic timeline. That's why the calibration of James Webb Space Telescope is so precise. Its instruments are tuned to catch these faint signatures without distortion. Every mirror segment, every detector, every line of code is part of a system built for accuracy at unimaginable distances. This is why the oxygen signature was not a guess. It was a precise measurement, the kind that locks a galaxy to its place in history. This is why Webb is more than a telescope, it's a time machine. By reading these tiny shifts, astronomers can place objects onto the cosmic timeline with extraordinary accuracy. Each spectral line is like a mile marker on a road stretching back to the beginning. For the oxygen signal, that marker sits in the earliest era of galaxy formation. No matter how the data is checked or who examines it, the conclusion is the same. The light has travelled across almost the entire age of the universe to tell its story. And that story does not fit neatly into the timeline we built. The more astronomers examined the data, the more consistent it became. Each independent measurement, each check against background noise told the same story. This was not a faint or fragile detection. The oxygen signal was bright, stable, and precise. At such extreme distances, random noise usually muddies the picture. But this galaxy's spectrum had none of that confusion. It was cleaner than most objects found much closer. That clarity made the discovery even harder to dismiss. It wasn't hiding at the edge of uncertainty. It was standing in plain sight. The stronger the signal, the harder it is to explain away. Normally, faint galaxies at such distances push the limits of what telescopes can detect. But this one stood out with unusual clarity. That's what makes it so difficult to fold back into standard models. If it were noisy, astronomers could argue. If it were weak, they could doubt. But it isn't. It's solid, bright, and perfectly placed in time. The observation sits like a cornerstone, and everything built on current cosmology must now reckon with it. A single line of light has become a problem no one can ignore. When Webb detects light from the early universe, it doesn't just take a picture, it captures time itself. Every photon carries a timestamp, a record of the moment it left its source. For this galaxy, that moment came less than 300 million years after the Big Bang. That places it among the earliest objects ever recorded. This is not a realm where measurements are casual. The slightest shift can reshape entire models of cosmic history, and yet the data for this object held firm, its signal anchored deep in the universe's first chapter. The timeline, however, refuses to cooperate. This is the heart of the paradox. The chemistry of this galaxy belongs to a universe much older than the one that existed when its light was born. It's like discovering a full-grown tree in a forest that's barely sprouted seeds. Everything about it screams maturity, but the timeline whispers infancy. That gap isn't a rounding error or a minor inconsistency. It's a direct clash between observation and theory. Either something about early star formation moved at incredible speed, or something about our understanding of time in the early cosmos is incomplete. To understand why this clash matters, we need to look at how cosmic history is built. Astronomers don't just guess the age of the universe, they read it in the light. Every element leaves a unique imprint, a pattern of lines that act like a timestamp. When these patterns appear earlier than they should, it doesn't just stretch a theory, it threatens to rewrite it. That's why this galaxy has become a focal point. Its light isn't simply old. It is too old and too rich in elements to fit comfortably inside the current timeline. This kind of contradiction shakes more than just a few equations. The standard model of cosmology rests on the idea that galaxies grow gradually, that chemical enrichment takes time. If a young galaxy can skip ahead, then either the timeline of enrichment is wrong, or the early universe behaved in ways we have not yet uncovered. For astronomers, this isn't just a puzzle, it's a warning flag. A single galaxy out of place can ripple across the entire structure of cosmic history, forcing us to reconsider how the first stars, the first galaxies, and the first heavy elements came to be. This is not the first time observations have forced cosmology to bend. Throughout history, the universe has repeatedly surprised us. We once thought the cosmos was static. Then we discovered its expansion. We thought galaxies formed slowly over long stretches of time. Now a single oxygen line is hinting at something faster, sharper, stranger. Each time the universe breaks our expectations, it pushes science forward. And this galaxy might be doing exactly that, exposing a flaw in the way we measure time at the edge of creation. The question now isn't just what this galaxy is, but what it means. If it truly formed and enriched itself so early, then our models are missing something fundamental. Maybe star formation was more efficient. Maybe gravity worked differently in those first moments. Or maybe entirely new physics is hiding in plain sight. Whatever the answer, this tiny ancient galaxy has opened a crack in the timeline, and through that crack, a different story about the birth of the universe may emerge, one we have yet to fully grasp. The timeline problem doesn't stop with a single galaxy. Webb has uncovered several other distant objects showing the same surprising maturity. Each one sits at the edge of cosmic dawn, glowing more brightly and carrying more heavy elements than expected. This isn't a coincidence, it's a pattern. The more galaxies that fit this mold, the harder it becomes to explain them away as outliers. If they are real, then something fundamental about how the early universe grew must change. A few strange galaxies can be ignored. A whole population cannot. Each new detection chips away at the comfort of existing models. If these galaxies are common, then the early universe was far more efficient at building stars and forging elements than we've ever imagined. That means the cosmic clock we've trusted for decades may be off, at least during its earliest ticks. This is how revolutions in cosmology begin, not with noise, but with quiet, undeniable patterns. A single galaxy started the question. A growing crowd is demanding an answer. The idea that multiple galaxies share this early maturity is more than a curiosity. It's a problem. One anomaly can be explained away. A pattern demands explanation. If so many galaxies are chemically advanced so soon after the Big Bang, then something about our timeline for element formation is incomplete. This isn't just about one oxygen line. It's about an entire population speaking the same language of accelerated growth, and that language is getting louder with every new observation. The universe was supposed to take its time. Stars were meant to form slowly, enriching their surroundings over countless generations. But these galaxies suggest a different story. One where the first cycles of star birth and death happened at breakneck speed. This would mean that heavy elements like oxygen, carbon and iron became widespread far earlier than expected. If true, it reshapes the early timeline of cosmic evolution and forces us to reconsider how fast the universe can build complexity out of nothing. If the early universe really forged stars and elements this quickly, it forces us to rethink the conditions at the beginning. Perhaps the gas clouds were denser, collapsing faster under gravity's pull, or maybe the stars themselves were different, hotter, larger, and far more efficient at enriching their surroundings. Whatever the mechanism, it must explain not just one anomaly, but an entire pattern of galaxies shining too brightly too early. That's the challenge now facing cosmology. To explain how the universe grew up so fast. This is where theory lags behind observation. Simulations of the early cosmos struggle to reproduce galaxies with this much oxygen so soon after the Big Bang. Even when parameters are pushed to their limits, the predicted chemical enrichment falls short. To match the data, something must be added, a missing ingredient in the recipe of cosmic evolution. It might be a subtle adjustment, or it might demand a complete rewrite of how the first stars lived and died. Either way, the timeline will not stay the same. Oxygen is not just a chemical curiosity, it's a storyteller. It doesn't appear in the Big Bang. It's forged in the cores of massive stars as they burn through their fuel and cast their ashes into space. To find oxygen in a young galaxy is to find the fingerprints of entire stellar generations that lived and died in a cosmic instant. This makes the signal more than a simple detection. It's direct evidence of how far the universe had already come in just a few 100 million years. That is why oxygen matters so deeply in cosmology. It's one of the earliest heavy elements to form, and it spreads quickly through stellar explosions. Where oxygen exists, stars have already lived, burned, and collapsed. It's a marker of maturity. In this galaxy, the oxygen line isn't faint or tentative. It's strong, clear, confident. That means the stars responsible for it weren't rare anomalies. They were plentiful enough to change their surroundings fast. And that speed is exactly what shouldn't have been possible at this point in time. To understand how extraordinary this is, we need to follow oxygen's journey. It begins inside massive stars forged during the final burning stages of their short, intense lives. When those stars reach the end, their cores collapse, triggering titanic explosions. In those moments, oxygen is ripped from their interiors and hurled into the surrounding space. That material mixes with nearby gas clouds, enriching them. From this enriched gas, new stars are born, stars with the chemical memory of their predecessors. Each cycle builds more complexity into the cosmos. But normally this takes time. A lot of time. The oxygen we see in this galaxy means that these cycles didn't unfold slowly. They happened in rapid succession. First-generation stars must have formed, lived, and exploded almost immediately. Their ashes had to cool and condense into new stars with incredible speed. It's as if the universe skipped the slow part of its growth and sprinted straight into maturity. That is what makes this detection so powerful. It doesn't just speak of stars. It speaks of time itself compressed into a window so small it defies our expectations. In the standard picture of cosmic evolution, this process unfolds gradually. First-generation stars enrich their surroundings over tens or even hundreds of millions of years. Oxygen builds up slowly like a long sunrise, but the signal from this galaxy tells a different story, one of acceleration. If the enrichment happened this fast, then either the stars formed at an extreme rate, or some hidden factor amplified their impact. In both cases, the result is the same. The early universe was far more dynamic than expected. This rapid pace shakes the foundations of existing models. Current simulations can't match this kind of chemical growth so soon after the Big Bang. Even the most optimistic scenarios still fall short. To bridge the gap, something in our understanding must shift. Either stars were forming faster than we think, or the processes that spread their elements were far more efficient. Whichever it is, the oxygen in this galaxy is forcing cosmology to face its limits. In the end, this mystery isn't just about one galaxy, it's about everything we think we know about time in the early universe. The cosmic timeline has always been built on a simple foundation. Stars form, slowly enrich space gradually, and galaxies grow step by step. But this object and others like it break that neat story. They tell us that the cosmos was busy much earlier than we believed, that the first stars didn't just flicker into existence. They ignited entire chains of events almost instantly. Something accelerated the beginning. Something moved faster than our models allow. The implications are profound. If early galaxies matured so quickly, then the timeline of cosmic evolution may be fundamentally wrong. The rules we've trusted for decades may only describe a slower later universe, not its fiery birth. This is why astronomers are staring at a single oxygen line with such intensity. It's not just a detail, it's a doorway. whatever is waiting on the other side could reshape how we understand the first moments of everything, the very architecture of time itself. This tension between data and theory is exactly how science advances. A single discovery may start as an outlier, but if it holds up under scrutiny, it becomes the spark that forces the entire field to adapt. James Webb Space Telescope was built to peer deeper into time than any instrument before it. In doing so, it may have stumbled on something profound, a universe that grew faster than we believed possible. This is more than just a strange galaxy. It's a window into a chapter of cosmic history we thought we understood but clearly do not. For cosmologists, this is both thrilling and unsettling. The models that describe the birth of galaxies and the growth of elements are among the most trusted frameworks in astrophysics. They've explained everything from nearby galaxies to distant quasars, but now a quiet signal of oxygen from the cosmic dawn has begun to press on their edges. Whether the solution lies in faster star formation, altered physics, or something entirely unexpected, this discovery has already achieved one thing. It has made us question the story we've been telling about the beginning. Every discovery that breaks a timeline is an opportunity. When observation outpaces theory, it doesn't mean the science has failed. It means the universe is revealing something new. This distant oxygen signal isn't just bending the edges of our models, it's cutting straight through their core, demanding a better explanation. The timeline we've built for cosmic evolution is elegant but fragile. It's based on the idea that everything has a rhythm. Stars form, die, enrich and repeat. But if galaxies were already mature so early, then that rhythm was never as slow as we thought. Something in the score is missing a beat. This realization forces astronomers to look beyond their comfort zones. Perhaps star formation was far more explosive at the dawn of time. Perhaps gravity sculpted galaxies faster, or energy flowed differently through primordial gas. Or maybe the very assumptions about how the early universe behaves need to be rewritten. Whatever the answer, this small ancient galaxy has become a key turning point. Its light has travelled across nearly the entire age of the universe, not just to be seen, but to challenge everything we thought we knew about how cosmic history began. The deeper we look into the early cosmos, the more it behaves like a story we only half understand. For decades, cosmology has relied on carefully built models that matched observation almost perfectly. The formation of stars, the build-up of elements, the growth of galaxies, everything seemed to follow a predictable rhythm. But the James Webb Space Telescope has revealed pages that don't match the script. This isn't just a minor mismatch. The timeline at the dawn of structure may be fundamentally different from what we imagined. The first chapters of cosmic history might be far more compressed, more intense, more violent. If that's true, it means the universe raced through its formative years at a pace we've never accounted for. Star birth, chemical enrichment, and galactic assembly might have been happening in overlapping waves stacking on top of each other almost instantly. This forces a shift in perspective. Instead of a quiet dawn slowly brightening, we may be looking at a cosmic sunrise that erupted like a storm, fast, brilliant, and transformative. A single oxygen line might be the crack in the wall through which the truth is starting to shine. When models break, scientists have two choices: force the data to fit the theory, or reshape the theory to fit the data. In this case, the data isn't bending. The oxygen line is too clean, the signal too strong, the timeline too clear. That leaves only one path forward: rethinking the way we describe the birth of galaxies. This doesn't mean tearing everything down. It means widening the frame. Perhaps our models capture only part of the story, the slower middle chapters, while the true opening act was faster and more chaotic than we ever allowed for. This is how revolutions in science begin, not with loud declarations, but with quiet, undeniable contradictions. The early universe may have followed rules we've only glimpsed, shaped by conditions no longer present today. Each new observation from Webb doesn't just add another puzzle piece, it redraws the edges of the puzzle itself. And somewhere inside that shifting border lies the real story of how the first light rose out of the darkness. The key to solving this puzzle may lie in the first generation of stars. These giants forged from pristine hydrogen and helium lived fast and died violently. If they were far more massive and efficient than expected, they could have flooded their surroundings with oxygen in record time. A single generation of such stars could do the work we once thought required many. This idea would explain why these galaxies seem so chemically mature, but it also raises deeper questions about how such stars could have formed so quickly in such abundance. Forming stars that massive requires enormous gas reservoirs collapsing almost instantly, something we've never observed directly. If this was common in the early universe, it means the conditions back then were radically different from what we see now. These extreme stars might not only explain the oxygen, but also shape how galaxies themselves were assembled. In other words, they wouldn't just enrich the cosmos, they would define the entire pace of its early evolution. If these first stars were truly that extreme, they wouldn't have looked anything like the stars we know today. They would have burned hotter, shone brighter, and lived shorter lives, pouring out energy and radiation at unimaginable levels. Their supernovae would have torn through their surroundings, triggering more collapses, more star formation, and more enrichment, all in a rapid chain reaction. This kind of stellar frenzy could turn a young simple galaxy into a chemically complex one in a fraction of the expected time. But for this to work, everything has to happen at once. Gas must collapse quickly, stars must form efficiently, explosions must spread their elements without blowing the galaxy apart. It's a delicate dance at cosmic scale, and somehow it happened. If such stellar chains were common, they might explain why so many early galaxies defy the standard timeline. What we thought was a quiet beginning may have been a short, violent storm of creation that set the pace for everything that followed. This picture of a fast, violent beginning is both elegant and unsettling. It suggests the early universe didn't slowly build its structures, it detonated into complexity. In just a few 100 million years, massive stars formed, burned out, exploded, and seeded the cosmos with the raw material for everything to come. If this is true, then galaxies weren't quiet nurseries, but fiery forges roaring with energy. It's a vision that changes how we imagine the cosmic dawn, not as a soft glow, but as a storm of light and matter. But even this explanation has limits. Extreme star formation alone may not fully account for the oxygen levels we observe. The numbers still strain against the timeline. That means either our understanding of how fast stars can form is incomplete, or something even stranger is shaping those first galaxies. Perhaps there are hidden factors, subtle physical processes that allowed the universe to sprint through its first steps faster than we ever thought possible. And Webb's sharp eyes might be the first to reveal them. Some astronomers suggest that the answer might lie not in the stars themselves, but in the environment that birthed them. If the first gas clouds were far denser and colder than current models, predict they could have collapsed into stars with incredible efficiency. Gravity would have had less resistance to overcome, allowing star clusters to form almost all at once. This would create a cosmic chain reaction. Faster collapses, faster star formation, and earlier chemical enrichment. It wouldn't break physics, it would simply reveal that the early universe was far more extreme than the quiet cosmos we observe today. But if that's true, it raises new questions about what conditions made this possible. Was the early gas different in ways we haven't accounted for? Were there unseen forces or interactions at play? Or were the physical rules the same, just operating in an environment more intense than anything we can replicate now? Answering these questions will take more than one discovery. It will require peeling back the first layers of cosmic history, one faint line of light at a time. An oxygen silent and glowing may be the key. If denser gas clouds really fueled this early frenzy, then the early universe wasn't just faster, it was fundamentally different. Star formation wouldn't have been limited by the slow regulated processes we see in modern galaxies. It would have erupted like a chain of firecrackers, each ignition triggering the next. That could explain why so many galaxies appear chemically evolved when the universe was still a child. This scenario paints a picture of a cosmos sprinting, not strolling through its infancy. A timeline once thought stable now looks fragile. But even this more intense environment must follow physical laws. There are limits to how fast gas can cool, how quickly stars can ignite, and how far elements can spread. If the early universe really pushed those limits, then we're standing at the edge of what our current physics can explain. And that's what makes this discovery so powerful. It doesn't just give us answers. It points toward the boundary between what we understand and what we have yet to uncover. The early cosmos may have been far less orderly than we imagine. Modern galaxies are shaped by stable feedback loops, gas flows, star formation, enrichment, and regulation. But in the beginning, those loops may not have existed yet. The first galaxies could have grown in bursts, devouring their fuel rapidly and shining fiercely for a brief moment before settling into calmer rhythms. This chaotic infancy would naturally produce galaxies that looked too old for their age, their chemical fingerprints already rich while the cosmic clock was still barely ticking. If this picture is correct, the timeline problem may not point to a broken law of physics, but to an era we've misunderstood. A universe without regulation would move at breakneck speed, burning through its early growth, before slowing down into the stable structures we see today. It's a sobering thought. What we call normal cosmic evolution might only describe a later chapter of the story. The first pages, the ones Webb is finally reading, were far wilder, louder, and faster than we ever expected. This vision of a wild, unregulated early cosmos fits the evidence, but it also challenges our instincts. Scientists like order. We build models that make the universe feel predictable, structured, measurable. But the light from these galaxies suggests the opposite, a young universe that burned through its first acts with reckless speed, leaving chemical traces far ahead of schedule. If star formation once ran unchecked, the galaxies Webb is seeing aren't exceptions. They're snapshots of a normal but short-lived era we've never witnessed before. This is the kind of discovery that doesn't just adjust numbers, it rewrites assumptions. It forces cosmologists to face the idea that their timeline may have always been incomplete. The oxygen line isn't just a detail buried in the data, it's the edge of a new frontier, one that blurs the line between what is known and what remains hidden. And beyond that edge, the early universe is waiting fast, fierce, and nothing like the gentle dawn we once imagined. If these galaxies reflect a universal phase rather than rare exceptions, then the timeline paradox becomes a clue, not a contradiction. It suggests the early universe wasn't broken. Our understanding of it is. For decades, cosmology has relied on a neat sequence: slow star formation, gradual enrichment, steady growth. But this sequence may describe only the middle of the story, not the beginning. The first act, as the oxygen tells us, was far more intense, a universe rushing to build itself in record time. This realization carries weight. It means the timeline problem might not be solved by small adjustments or clever tweaks. It might require an entirely new way of thinking about how galaxies emerge from darkness. Perhaps the early cosmos was tuned for speed, a perfect storm of density, temperature, and gravity that made everything happen at once. And now, billions of years later, those faint oxygen lines are the echoes of that storm still whispering their impossible story to us. The more we study these galaxies, the clearer their message becomes. The early universe was not the quiet, methodical architect we once pictured. It was an impatient builder throwing up its first structures at breathtaking speed. Every spectral line Webb detects is a fossil from that explosive era, carrying the memory of how fast the cosmos once moved. This pace doesn't break the rules of physics, it stretches them, revealing their edges. The universe was playing the same game, we know, just at a tempo we've never seen before. For astronomers, this changes the way the cosmic dawn is imagined. Instead of gentle starlight slowly painting the darkness, it may have been a blaze, a rapid cascade of star birth and chemical growth. A surge so brief and brilliant that its remnants now look out of place on our timeline. But they're not out of place. We've built our understanding on the slower rhythm of a mature cosmos. The early universe simply kept a different beat. The James Webb Space Telescope is revealing a chapter of the cosmos that theory had left blank. For decades, the early universe was imagined as slow, faint, and simple, a quiet beginning before the great constructions of cosmic history. But the light from these young oxygen-rich galaxies paints a different scene. It speaks of an era when everything happened fast before order could settle in. This is why a single spectral line matters. It's not just a measurement. It's a voice from a time we never thought we'd hear directly. What we once pictured as a gentle sunrise may have been more like a sudden blaze galaxies erupting into existence in rapid succession. The oxygen is proof of that fury etched into the light that has travelled across nearly the entire age of the universe. For astronomers, this isn't the end of a story, it's the beginning of a new one. A story that demands we rethink how quickly the cosmos can create, evolve and mature. The timeline isn't broken. It's deeper, faster and far more alive than we ever imagined. This is the quiet power of oxygen. It doesn't shout. It doesn't flare like a supernova. It simply waits etched into ancient light, carrying a record of a time when the universe moved faster than we believed possible. What we're seeing through James Webb Space Telescope isn't a glitch. It's the early cosmos speaking clearly for the first time. Every line in the spectrum is a sentence. Every measurement is a page in a story older than galaxies themselves. And we are finally learning to read it. This is why the discovery matters so deeply. It's not just about rewriting numbers in a model. It's about listening to what the universe has been saying all along. These galaxies aren't breaking the timeline, they're revealing the parts we left out. The early cosmos may have burned brighter, faster and wilder than we ever dared to imagine. And through this single, elegant element, it's letting us peek into those forgotten first moments. For cosmology, moments like this are rare. Most discoveries confirm what we already expect, tightening the details of an established picture. But sometimes the universe refuses to behave. It drops a clue so sharp and undeniable that it cuts through decades of certainty. This oxygen signal is one of those clues. It doesn't fit inside the familiar story of slow measured cosmic evolution. Instead, it whispers of something swifter, stranger, an opening act that refuses to be ignored. This is how new eras in science begins, not with grand theories written in stone, but with small stubborn facts that won't go away. Each spectrum Webb collects adds pressure on the old timeline, pushing cosmologists to widen their view. The early universe isn't broken. It's simply more alive than we ever imagined. And if we're willing to follow where this oxygen line leads, it may carry us into an entirely new understanding of how everything began. Science advances when the universe refuses to behave. The James Webb Space Telescope was designed to answer questions, but sometimes it asks bigger ones in return. A single oxygen line from a small ancient galaxy has forced cosmologists to look deeper, question harder, and rebuild their sense of time. This isn't just about refining models. It's about confronting the fact that the early universe was nothing like the calm, gradual evolution we once imagined. It was fast, fierce, alive. This revelation doesn't diminish what we've learned, it expands it. Every timeline is a map, and Webb has shown us where ours was missing entire continents. What we mistook for anomalies are actually windows into a forgotten era. In those first few 100 million years, the cosmos sprinted ahead, writing a chapter we're only now beginning to read. And oxygen, quiet and precise, is the key that unlocked that hidden story. Every telescope changes how we see the universe. James Webb Space Telescope may have done something far greater. Change how we think about time itself. For years, the cosmic timeline felt settled, a steady sequence of starbirth enrichment and galactic growth. But this single oxygen signal cracked that certainty. It forced us to consider a beginning far more intense than the models predicted. A universe not just awakening, but racing toward complexity almost as soon as it existed. This discovery doesn't close a chapter, it opens one. Each new galaxy Webb uncovers at the edge of cosmic dawn sharpens the picture of a universe built in haste. And each spectral line adds weight to the idea that our timeline is only a fragment of the truth. The early cosmos was not a quiet place. It was a storm of light, heat and motion. And now, after more than 13 billion years, we're finally listening to what it's been trying to tell us. The most remarkable part of this discovery is how quiet it is. No new particle, no explosive signal, just a thin, bright line of oxygen from the edge of cosmic dawn. But within that line lies the power to reshape the entire story of how the universe began. James Webb Space Telescope wasn't built to find easy answers. It was built to confront us with truths hidden in plain sight, and this truth is clear. The early cosmos was never slow. It raced towards structure with astonishing speed. This is the kind of moment that redefines fields. Just as past generations rewrote the universe after learning it was expanding, today's astronomers may rewrite it again, this time because of how fast it grew up. The timeline isn't failing us. It's inviting us to look closer, to understand more, to build something new. And at the center of this invitation is a whisper of oxygen, a silent witness to the most frantic, beautiful beginning imaginable. Every time the universe has surprised us, it has forced science to grow. When galaxies were first discovered to be racing away, it gave birth to modern cosmology. When cosmic background radiation was found, it rewrote our understanding of the Big Bang. And now a single oxygen line may be doing the same. It's a quiet discovery with loud consequences. It suggests that our timeline, a cornerstone of cosmic history, may need to be rebuilt from its foundation upward. This is what makes astronomy so powerful. We don't just look at stars to admire them. We use their light to measure the shape of reality. The early universe is no longer a shadowy guess. It's becoming a sharply lit stage where the first actors performed much faster than expected. The oxygen line isn't just rewriting a timeline, it's revealing how much more there is to learn. The beginning of everything is closer, brighter, and far more explosive than we thought. What makes this moment so striking is its simplicity. No exotic particle, no sudden contradiction in mathematics. Just a clean, bright oxygen signal that refuses to fit neatly inside the model. Sometimes that's all it takes to reshape our view of the universe. This single line challenges the slow, carefully layered story of early galaxy growth. It points instead to a beginning that burned hotter and moved faster, an opening act that's been hiding in plain sight for billions of years. Every major leap in cosmology has started with evidence like this, small, precise and stubborn. The data doesn't need to shout to be undeniable. Webb's infrared eyes have peeled back another layer of the cosmic curtain, revealing a universe that didn't wait politely for structure to emerge. It sprinted, it roared, it built galaxies at a pace that bends our understanding. And now piece by piece we are catching up to what it has always been. Every generation of astronomers faces a moment like this when the data doesn't match the story they've built. The James Webb Space Telescope has given us that moment again. A single oxygen line has cracked open the most carefully timed sequence in cosmic history, revealing that the early universe was not patient. It was a sprinter. This isn't the kind of evidence that fades with better measurements. It's the kind that forces us to rewrite entire chapters of how galaxies were born. That's why astronomers keep returning to this discovery. Not because it's mysterious, but because it's precise. It's stable, repeatable, and uncomfortably clear. It doesn't bend under scrutiny. It just sits there quietly, daring us to explain it. And that challenge is what drives science forward. We thought we understood the first few 100 million years after the Big Bang. Now, thanks to this small glowing line, we know we've only been reading part of the book. This isn't just a story about oxygen or distant galaxies. It's about how the universe reveals its secrets, not with grand gestures, but with quiet, precise clues. A single spectral line has opened a door to an age we thought we understood, only to find the timeline bending beneath our feet. James Webb Space Telescope wasn't built to confirm what we already knew. It was built to show us what we missed. And this discovery proves just how much that is. The early universe has always been a blur, a distant whisper at the edge of visibility. But now with Webb's eyes, that whisper is becoming a clear, unshakable signal. We can no longer picture cosmic dawn as quiet or slow. Instead, we see a storm of light and creation that raced ahead of our expectations. A storm so fast and so bright that it left behind traces even 13 billion years later, waiting for us to finally notice. What began as a quiet observation has become a challenge to the heart of modern cosmology. A single oxygen line, precise, stable, undeniable, has revealed that the early universe was not the slow, methodical architect we once believed it to be. Instead, it built its first galaxies with astonishing speed, leaving behind evidence that's only now reaching us. The James Webb Space Telescope has not just expanded our view, it has shattered the edges of the map we trusted. This is why this discovery carries such weight. It doesn't just tweak numbers, it rewrites context. Everything we thought about how fast galaxies could grow, how early stars could form, and how the cosmos unfolded is now under new scrutiny. And through it all, the oxygen line remains quiet, unwavering. It is the kind of evidence that doesn't fade over time. It waits, demanding that we catch up to a universe that has always been one step ahead of us. Every great scientific turning point begins with a moment like this, a simple, stubborn fact that refuses to be ignored. The timeline of cosmic history was supposed to be solid, each chapter in order, but the oxygen line has slipped between those chapters, showing us that the universe tells its story at a faster pace than we expected. James Webb Space Telescope didn't just peer into the past, it caught the cosmos in the act of rewriting its own beginning. This is why astronomers speak of this discovery with a mix of wonder and unease. It doesn't simply add a footnote to existing theory, it bends the timeline itself. The early universe, once imagined as calm and gradual, now looks fierce and restless. The quiet signal of oxygen stands like a marker in the dark, pointing back to an age we only thought we understood. And now we must follow where it leads. The timeline problem is no longer just a puzzle for a few astronomers. It's becoming one of the biggest questions in modern cosmology. A single oxygen line captured with precision has pulled at the threads of a story we thought was solid. Now those threads are beginning to unravel, revealing something bigger beneath. James Webb Space Telescope didn't just open a new window into the past. It may have cracked the frame that held the entire timeline together. And yet, that's exactly how science moves forward. Every revolution begins with a quiet piece of evidence that refuses to be ignored. The universe is not contradicting us, it's correcting us. This oxygen line is more than data. It's a doorway to a faster, fiercer version of the early cosmos. A reminder that the universe has always been bigger, stranger, and more brilliant than the stories we build to contain it. Astronomers have faced timeline shifts before, but this one is different. The evidence isn't vague or debatable, it's clean, sharp, and relentless. The early universe, once thought to be slow and empty, is now revealed as fast and crowded. Galaxies formed, stars burned, and elements spread through space in a fraction of the time models predicted. This isn't just a revision of cosmic history, it's a reminder that the universe writes its own story, and we are only beginning to learn how to read it properly. The oxygen line sits at the heart of this revelation like a bookmark in time. Every analysis, every check, every alternative explanation has only made it clearer. The early cosmos wasn't late to the party, we were late to understand it. And now with James Webb Space Telescope listening so carefully, those first pages of cosmic history are finally speaking. Their message is simple. The universe was ready long before we were. The deeper we look, the clearer it becomes that this isn't just an astronomical finding, it's a turning point. A single oxygen line has peeled back the veil on a period of cosmic history we thought we understood. Now every model must either adapt or fall behind. James Webb Space Telescope has done exactly what it was meant to do. Not just observe the past, but rewrite our understanding of it. And the first chapter to change is time itself. This is what makes this discovery so powerful. It doesn't shout. It simply waits, carved into ancient light, undeniable and unshakable. And like every great shift in science, it began with something small. A single galaxy, a single line of oxygen, a message carried for more than 13 billion years. It's not just challenging our timeline, it's inviting us to see the universe the way it truly was. Fast, fierce, and breathtakingly young, every great discovery in cosmology has a moment where the story splits. Before and after. Before this oxygen line, the early universe was a place we described with comfortable certainty. Quiet, gradual, slow. After it, we face a different image. Galaxies racing into existence, stars igniting in rapid waves, and chemical fingerprints appearing far too soon. James Webb Space Telescope didn't just show us a distant galaxy. It showed us the speed at which the cosmos was built, and now that the door has opened, we can't look away. Each new observation will either reinforce or reshape this emerging story, but the foundation has already shifted. This discovery is not a footnote, it's a pivot point, a reminder that the universe is always larger and stranger than the narratives we create to explain it. The timeline hasn't failed. It has evolved, revealing the beating heart of a younger, wilder cosmos. A timeline is only as strong as the evidence behind it. For years, cosmology built its foundation on a slow, predictable sequence. But now a single oxygen line has struck at the core of that certainty. James Webb Space Telescope has pulled back the curtain on a universe that wasn't waiting for anyone. It was racing ahead, carving galaxies from darkness almost as soon as it was born. This is more than a discovery, it's a reordering of how we measure time itself. The early universe no longer fits inside the neat timeline we once trusted. And that's what makes this moment so powerful. The cosmos isn't contradicting us out of spite. It's revealing the limits of our imagination. Through this single signal, we're seeing the universe not as we expected, but as it truly was. And that gap between expectation and reality is where every great leap in science begins. One of the leading explanations for this accelerated evolution involves a top-heavy initial mass function, a distribution where the first generation of stars was skewed heavily toward massive ones. Unlike ordinary stars, these giants burn fast and enrich their surroundings quickly. A single wave of such stars could produce the oxygen Webb detected without needing multiple generations. If this model is correct, it suggests that the early universe favored the birth of massive stars far more than it does today, fundamentally altering how galaxies evolved at the dawn of time. A top-heavy IMF would explain several anomalies at once. Rapid enrichment, unexpected brightness, and fast structural growth in young galaxies. It would mean the early cosmos was dominated by short-lived titans whose explosions seeded their environments almost immediately. This idea is already being tested through new simulations, pushing star formation models beyond the limits of modern galaxies. If confirmed, it would reshape our understanding of how quickly the building blocks of cosmic structure appeared. Another possible explanation focuses on feedback mechanisms in the early universe. When massive stars die, their supernova explosions don't just enrich space, they also compress nearby gas, triggering new star formation. If this feedback loop operated more efficiently and the dense conditions of the early cosmos galaxies could have experienced multiple stellar cycles in rapid succession, this would accelerate oxygen buildup dramatically, creating the chemical signatures Webb now detects in galaxies far too young to match traditional models. In this scenario, enrichment isn't a long linear process. It's a chain reaction. One explosion ignites another wave of stars, which leads to more enrichment, and the cycle repeats. High gas densities and weaker regulatory processes in early galaxies may have amplified this effect. Such runaway starbursts would explain how a galaxy could become chemically mature in just a few 100 million years, bypassing the slower regulated evolution that dominates the modern universe. A third hypothesis explores the idea of enhanced cooling mechanisms in the early universe. For gas to collapse into stars rapidly, it must cool efficiently. In modern galaxies, metals help radiate heat away, but in the primordial cosmos there are no metals yet. Some theorists propose that molecular hydrogen and exotic cooling channels may have allowed gas to lose energy faster than expected. This would lead to earlier and more intense star formation even without multiple stellar generations. If this mechanism operated efficiently, it could explain how massive star clusters formed so quickly, triggering rapid enrichment and galaxy growth. Simulations suggest that even small differences in cooling rates at that epoch can drastically accelerate the timeline. This theory doesn't contradict known physics, it adds nuance. It suggests the first galaxies might have been shaped not just by star formation itself, but by the hidden thermodynamics of primordial gas. A fourth line of investigation looks at early merger activity. In the young universe, galaxies were much closer together. Frequent collisions and mergers could have accelerated star formation dramatically, as gravitational shocks compressed huge reservoirs of gas. These intense bursts would naturally enrich the surrounding environment faster than isolated galaxies could. This would also explain why many early galaxies appear unusually bright. Mergers feed them with new fuel, driving rapid growth in both mass and chemical complexity. Modern galaxies still merge, but at a much slower pace. In the dense early cosmos, this process would have been nearly constant, triggering repeated starbursts in very short intervals. Each collision effectively rewinds the clock, giving the galaxy another chance to accelerate its evolution. This idea aligns well with existing simulations and provides a natural pathway to explain how oxygen signatures became so strong so early in cosmic history. It suggests that galaxy interactions, not just star formation physics, shaped the first timeline. Another avenue of research involves gravitational potential wells created by massive dark matter halos in the early universe. If these halos assembled faster than expected, they could have trapped vast amounts of gas early on, making it easier for galaxies to grow rapidly. A deeper gravitational well means stronger gas inflows and more intense star formation. This would give young galaxies the resources needed to reach high levels of oxygen enrichment in just a short time, far earlier than standard models predict. This explanation shifts the focus from star physics to structure formation. If dark matter halos formed quickly, they could act as cosmic engines, pulling in gas at rates far higher than what we see today. Such rapid assembly would allow a single galaxy to behave more like a cluster forming stars at a furious pace. It would also fit with observations that many early galaxies are surprisingly massive for their age. If the halos came first, the galaxies could grow up fast inside their deep gravitational wells. A related hypothesis looks at cold gas accretion, narrow streams of pristine gas flowing directly into young galaxies from the cosmic web. Unlike mergers, which are chaotic, these cold flows provide a steady and efficient supply of star-forming fuel. If they were more intense in the early universe, they could sustain extreme starburst activity over long periods without exhausting the gas reservoir. This mechanism could explain how early galaxies maintained rapid growth and chemical enrichment without falling apart under their own energy output. Simulations of the cosmic web already hint at these cold flows feeding massive galaxies at high redshifts. Their efficiency would allow stars to form faster than feedback could shut the process down. Combined with massive halos, this creates a perfect environment for accelerated evolution. If confirmed, cold accretion could become a key piece of the puzzle, showing how galaxies grew explosively without needing exotic physics, just the raw dynamics of the young cosmic web itself. Some researchers have also pointed to variations in the cosmic microwave background temperature as a subtle but powerful influence. In the early universe, the background was warmer, which affected how gas cooled and collapsed. This slightly higher temperature could create a unique balance, warm enough to keep molecular hydrogen from freezing out, but cool enough to let massive clouds collapse efficiently. The result would be a natural boost in early star formation, helping galaxies build their chemical signatures faster than they can today. This explanation doesn't rely on exotic new physics. It simply acknowledges that the environment of the early cosmos was fundamentally different. A warmer background meant different cooling thresholds, different gas dynamics, and potentially more favourable conditions for rapid starburst activity. Even small shifts in temperature can have outsized effects when dealing with massive gas clouds on galactic scales. This might have quietly accelerated the entire timeline without leaving behind anything, except the oxygen lines we're seeing now. Another factor that may have pushed the timeline forward is metal-free star formation efficiency. The first stars made purely of hydrogen and helium didn't have to compete with dust or metals for cooling channels. That allowed gas to fall directly into star-forming regions with minimal resistance. These stars could form in clusters that were larger, denser, and faster than anything typically seen in the modern universe. This rapid assembly would naturally lead to stronger oxygen signatures within a few stellar cycles. Unlike later generations, these primordial stars likely produced vast amounts of ionizing radiation and ended their lives in extremely energetic supernovae. Their explosive deaths enriched their surroundings almost instantly. If this process repeated just a few times, it would explain the early maturity of the galaxies Webb observes. This model aligns well with predictions about the first stellar populations, suggesting that the physics of metal-free stars alone may have been enough to shift the entire cosmic timeline forward. A further piece of the puzzle may involve pair instability supernovae, violent explosions of extremely massive metal-free stars. These events are far more powerful than ordinary supernovae, releasing enormous amounts of oxygen and other heavy elements into their surroundings in a single burst. If such stars were common in the early universe, a single generation could enrich galaxies to levels we once thought impossible at that age. This would make the chemical maturity of these galaxies less mysterious, and more a natural outcome of extreme stellar physics. Pair instability supernovae occur in stars hundreds of times more massive than the Sun. Their yields are enormous, and they leave behind no remnant, just a cloud of newly forged elements. A wave of these explosions would fill young galaxies with oxygen and other metals almost immediately. This scenario fits well with the top-heavy IMF idea, offering a concrete mechanism for the enrichment. If proven, it would mean the early universe's chemical story was written not slowly but in spectacular explosive bursts. Another critical element in this timeline puzzle involves cosmic reionization. As the first stars and galaxies flooded space with ultraviolet radiation, they ionized the surrounding hydrogen, altering the behavior of gas flows. Ionized gas is easier to heat and move, which may have allowed galaxies to draw in fresh material faster and sustain rapid star formation. This process unfolding just a few 100 million years after the Big Bang could have accelerated both growth and chemical enrichment across large regions of the universe. Reionization is often treated as a byproduct of galaxy formation, but it may also have fed back into the process, amplifying it. Galaxies didn't just create radiation, they were shaped by it. By changing the temperature and pressure of the intergalactic medium, reionization could have made it easier for gas to flow inward and form stars faster. This feedback loop would help explain why oxygen signatures appear so strong and widespread at such an early time, turning cosmic reionization into both an effect and a driver of rapid evolution. One more possibility comes from runaway star cluster formation. In this scenario, once the first stars form, their gravity pulls in nearby gas, rapidly creating dense clusters that grow almost explosively. Unlike the slow regulated formation in modern galaxies, these early clusters could convert a huge fraction of available gas into stars in just a few million years. Such runaway events would produce intense bursts of light, strong feedback, and a rapid injection of heavy elements like oxygen into their surroundings. These massive clusters would act like cosmic furnaces, burning through their fuel in a short but furious period. Their supernovae would enrich the interstellar medium at unprecedented speeds, allowing galaxies to appear chemically mature after only 1 or 2 stellar generations. If this mechanism was common, it would explain why Webb's observations reveal such high oxygen levels so early. The timeline wouldn't need to be broken. It would simply be faster powered by the runaway growth of the universe's very first star factories. In the end, everything comes back to a single line of oxygen, a quiet signal that shattered our neat timeline of cosmic history. The early universe was not slow. It was fast, brilliant, and full of furious creation. Stars were born in storms, galaxies rose in bursts, Oxygen, light and structure emerged far earlier than our models dared to allow. James Webb Space Telescope didn't just give us an observation, it handed us a question too large to ignore. What else have we misunderstood about the dawn of everything? This question points toward the next frontier. If galaxies grew so quickly, what does that mean for the formation of black holes, the birth of the first quasars, or the structure of the cosmic web itself? If the timeline is wrong for stars and oxygen, it might be wrong for everything that followed. Somewhere beyond these galaxies lies the next puzzle, the forces that shaped the universe's first giants. And that is where the next story begins, not with an answer, but with a new mystery waiting in the dark. Before the first galaxies took shape, before light truly filled the universe, something else may have emerged in the dark. When the cosmos was still less than 1 billion years old, some of the most powerful objects we know already existed, black holes with masses, millions, even billions of times that of the Sun. Their presence is a mystery. How could such giants form so early when the universe itself was still taking its first breaths? If stars were the builders of the cosmos, then these black holes were its ancient kings. They lurked at the centers of young galaxies, feeding on gas-bending light and shaping their surroundings with invisible hands. Today we can still see their distant glow, not directly but through the quasars they power. These ancient monsters are not just astronomical curiosities, they are windows into the universe's first moments, into physics pushed to its limit. And to understand them, we must follow the story back to where everything began, in the darkness after the Big Bang. The early universe was not a place of quiet creation. It was a landscape of rapid change, expanding, cooling, and assembling its first structures. Hydrogen and helium dominated everything. There were no planets, no galaxies as we know them, and no heavy elements to shape complexity. And yet hidden in that darkness, the seeds of the cosmos were being sown. The first stars were forming. Gravity was beginning to carve matter into islands of light. But gravity doesn't just build stars. It also builds monsters. The same forces that created the first bright points in the night could also drive matter inward, crushing it into invisible singularities. These early black holes would grow fast, too fast for our current models to explain. They should not have had enough time, and yet their light from billions of years ago reaches us today, blazing like beacons through the fog of cosmic dawn. To understand these ancient giants, we need to return to the first few 100 million years of cosmic history, an era astronomers call the cosmic dawn. The universe was still young, barely emerging from the darkness that followed the Big Bang. Matter had begun to clump under gravity, forming the earliest stars and galaxies, but scattered among these young structures were strange, brilliant beacons, quasars powered by black holes far too massive for their age. These quasars shine so brightly that they can outglow entire galaxies, making them visible across the cosmos. They are powered by black holes devouring matter at extraordinary rates. The puzzle is simple but profound. How could black holes grow so huge in so little time? Either our understanding of their formation is incomplete, or the early universe had pathways we've never fully grasped. This is the mystery scientists now chase across billions of years of light. The first clues came from the faint light of distant quasars. Astronomers found them shining from a time when the universe was less than 1 billion years old. Their brightness told a shocking story. At their cores were black holes already weighing hundreds of millions of suns. These objects didn't just exist, they thrived. They consumed matter faster than any known mechanism should allow, and their very presence meant something fundamental in our understanding was missing. Each quasar is like a time capsule preserving the state of the universe in its earliest chapters, and through these beacons we can trace the growth of black holes across cosmic history. But the numbers don't add up. Growing a black hole to such mass under known physical limits should have taken longer than the universe had been alive at that point. This is the paradox, one that forces us to question everything about how black holes are born. Among the most striking examples are quasars detected at redshifts greater than 7. Their light began its journey when the cosmos was still in its infancy. Observations reveal black holes with masses of nearly 1 billion suns already fully formed. These are not quiet objects. They blaze so powerfully that they pierce through the dense fog of the early universe. Their light has travelled for more than 13 billion years, carrying the signature of a time when galaxies were just beginning to form. What's even more unsettling is how common they seem to be. If these early monsters were rare accidents, we might dismiss them as cosmic flukes, but they appear again and again in deep sky surveys. Their abundance suggests a process not just possible but efficient. Something in the early universe allowed black holes to grow fast, perhaps even faster than we believed nature would permit. This is no isolated mystery. It's a pattern written across the cosmos. This mystery has transformed from a curiosity into a full-blown problem for cosmology. If these black holes truly existed so early, they must have formed and grown under conditions unlike anything we see today. Our current models, based on slow accretion and steady stellar evolution, simply can't keep up with the clock. It's as if these objects skipped the line of cosmic evolution, leaping ahead, while the rest of the universe was still getting started. That gap between what we observe and what our models allow is at the heart of the puzzle. Somewhere between the birth of the first stars and the rise of the first quasars, something extraordinary happened, and to solve it, we must go back to the beginning, to the chaotic first, hundreds of millions of years where matter flowed freely. Gravity reigned supreme, and black holes may have found a shortcut to grow. The timeline makes the problem clearer. The first stars are thought to have ignited roughly a few 100 million years after the Big Bang. Yet by the time the universe was less than 1 billion years old, some black holes had already reached enormous masses. This gives them only a few 100 million years to form, grow, and light up the cosmos as quasars, but under normal physics that's barely enough time to build a small galaxy, let alone a billion solar mass black hole. The speed required is staggering. These black holes must have grown at rates near or even beyond the theoretical Eddington limit, the balance point where radiation pressure should push back against infalling matter. For them to exist, something must have bent or bypassed those limits. Either their seeds were born massive, or the early universe offered growth channels that we have yet to fully understand. This is why astronomers call these objects cosmic monsters. Their existence isn't just impressive, it's disruptive. They don't fit neatly into the story we've built about how the universe grows. Instead, they force us to redraw the early chapters entirely. If black holes can grow this fast, then either we've underestimated the power of gravity, or we've missed key physical processes that existed only in the young cosmos. Every theory about the early universe must now account for these ancient giants, and that's why they've become one of the most important clues to understanding cosmic dawn. To solve the paradox, we must hunt for their origins. Were these black holes born from stars? Did they collapse directly from gas? Or did some of them come from an even stranger, more primordial source, one that predates galaxies themselves? To trace the origin of these ancient giants, we must begin with the concept of black hole seeds. Every supermassive black hole started as something smaller, a seed that grew over cosmic time. But these early quasars didn't have the luxury of billions of years. Their seeds must have been massive, or their growth unnaturally fast. Astronomers are now piecing together 3 major pathways. The first involves the death of the earlier stars, enormous metal-free suns collapsing into black holes, only a few dozen to a few 100 times the mass of our Sun. If they could accrete matter fast enough, these stellar remnants might grow into the giants we see. The second path suggests something more dramatic: direct collapse. Under the right conditions, massive gas clouds could skip star formation altogether and plunge inward to form black holes thousands of times heavier right from birth. The third and boldest points to primordial black holes forged in the chaos of the Big Bang itself. If they exist, they could be older than galaxies, older than stars, older than light itself. Each of these scenarios leads to a very different cosmic story. And to find the truth, we must explore them one by one. The simplest and most traditional idea is that the first black holes were born from the death of the universe's earlier stars. These were not ordinary stars. They were colossal, hundreds of times the mass of the Sun, and burned through their fuel in only a few million years. When they died, they collapsed into black holes, leaving behind compact seeds scattered across the young cosmos. These population 3 stars forged from pure hydrogen and helium were the first sources of light. Their deaths would have planted the earliest black holes into the dark fabric of the forming universe. From there, the seeds could have grown by pulling in gas dust and even merging with each other. This scenario is elegant because it doesn't require any new physics. It uses processes we already understand: star formation, stellar collapse, and accretion. But it also carries problem time. Starting from these small seeds, even under ideal conditions, might not be enough to explain billion solar mass black holes forming so early. Something more may have been needed to accelerate their growth. The problem with stellar remnants is scale. Even the most massive population 3 stars can only collapse into black holes a few hundred solar masses at most. To grow from there to a billion solar mass monster in less than a billion years would require uninterrupted, near-perfect feeding. The black hole would need to accrete matter at or above the Eddington limit almost continuously, but the universe is not so cooperative. Star-forming regions are chaotic. Feedback from radiation and supernovae pushes gas away, starving young black holes of fuel. Even under optimistic conditions, this steady growth would fall short. The math simply doesn't add up. This doesn't mean stellar remnants didn't play a role. They may have been the first seeds, the foundation, but on their own, they can't explain the sheer scale of the black holes we observe so early. Something else must have accelerated the process, something far more efficient than ordinary stellar death. This is why astronomers began exploring a more extreme possibility. What if some black holes were born big? Instead of starting from the death of stars, they might have formed directly from the collapse of vast, pristine gas clouds in the early universe. This is known as the direct collapse black hole scenario. In these rare regions, intense radiation from nearby star-forming halos could have suppressed normal star formation, allowing the gas to remain hot and stable. Without breaking up into stars, the entire cloud could collapse under its own gravity, forming a single massive black hole seed. Potentially tens of thousands of solar masses right from the start. If these seeds existed, they would have had a tremendous head start. They wouldn't need hundreds of millions of years to grow to quasar size. They'd already begin the race halfway to the finish line, feeding on surrounding gas to reach their enormous masses with ease. The direct collapse model has a powerful appeal because it solves the timeline problem elegantly. A seed of 10,000 solar masses doesn't need miraculous feeding rates to become a billion solar mass black hole within a few 100 million years. It just needs steady access to gas, something the dense early universe had in abundance. But forming such a seed requires special conditions. The gas must be metal-free, hot enough to resist fragmenting into stars and shielded from external cooling. These circumstances may have existed only in specific regions, making direct collapse a rare event. Yet rarity might be enough. Even if only a small fraction of early halos experienced these conditions, it could explain the number of quasars we observe at high redshifts. In this view, the first black holes weren't built slowly, they were born ready to dominate. The third and boldest idea reaches all the way back to the Big Bang itself. Some scientists propose that primordial black holes may have formed not from stars or collapsing gas, but from violent fluctuations in density during the universe's first moments. These would be objects born before galaxies, ancient relics of the universe's creation. If certain regions of space were just slightly denser than others, gravity could have crushed them directly into black holes. Unlike stellar remnants or direct collapse seeds, primordial black holes could have existed mere seconds after time began. If even a small population of them survived, they could have served as ready-made seeds for the supermassive black holes we see today. And if this idea proves true, it would mean these cosmic giants didn't just shape the universe, they were part of its birth. Each of these three pathways paints a very different picture of the early universe. Stellar remnants suggest a cosmos that builds slowly small seeds growing through persistence. Direct collapse implies a universe capable of taking shortcuts, creating massive black holes in a single catastrophic event. Primordial black holes push the mystery even deeper, tying their existence to the very beginning of space and time. It's possible that more than one of these pathways happened at once. The early universe was messy, chaotic, and full of extremes. Different regions may have followed different evolutionary tracks, producing a diverse population of black hole seeds. The real challenge is to find out which of these mechanisms or which combinations shape the monsters we observe at the cosmic dawn. That means studying not just black holes themselves, but the environments that gave birth to them. Understanding how these black holes grew so fast means confronting the ultimate constraint, the Eddington limit. This limit defines how quickly a black hole can accrete matter, before the outward pressure of radiation balances the inward pull of gravity. Under this rule, growth is steady but slow. Reaching 1 billion solar masses in a few 100 million years should be nearly impossible. Yet the quasars tell us it happened. Either these black holes started out far more massive than we thought, or they somehow broke the Eddington rules. Some theories suggest super Eddington accretion, where black holes briefly feed at rates above the classical limit driven by dense gas flows, or chaotic inflows that trap radiation. If this occurred in the early universe, it could give even small seeds a fighting chance to grow into the giants we observe today. And it might mean the laws we treat as rigid were in those early moments far more flexible. Super Eddington accretion isn't just a theoretical loophole, it may be a natural feature of the chaotic early cosmos. In dense gas-rich environments, infalling material can form thick accretion flows that trap radiation, instead of letting it push matter away. This allows black holes to gorge themselves far beyond the classical limit, growing at astonishing speeds. Some models suggest that if this feeding persisted even for short bursts, it would dramatically accelerate mass growth. A black hole could gain orders of magnitude in size over a relatively brief period. If early black hole seeds were embedded in such environments, super Eddington episodes could have acted like cosmic rocket boosters, turning modest seeds into giants, long before the universe was 1 billion years old. It's a process fast enough to match the timeline and wild enough to fit the early universe. But feeding isn't the only path to rapid growth. Black holes can also grow through mergers, the violent coalescence of two or more smaller black holes into one larger object. In the crowded early universe, galaxies were forming close together, colliding and merging in rapid succession. Their central black holes would likely have followed the same pattern. Every merger adds mass, and in some cases momentum. A handful of well-timed collisions between early seeds could quickly build up the enormous masses we see in ancient quasars. This scenario becomes even more compelling when combined with super Eddington feeding. Seeds formed from stars or direct collapse could merge and feed in overlapping bursts, compounding their growth. What might take billions of years today could have happened in mere hundreds of millions back then. Mergers also leave a distinct mark on the universe. When black holes collide, they unleash powerful ripples in space-time gravitational waves. These signals are faint today, but they carry the fingerprints of the first massive black holes. Detecting such waves from the cosmic dawn could reveal not just how fast these giants grew, but also how many collisions it took to make them. Future observatories like Laser Interferometer, SPACE, Antenna LISA are designed to listen for precisely this kind of signal. If LISA detects low-frequency gravitational waves from the early universe, it could confirm that mergers were a key accelerator of black hole growth. This would mean the story of the first black holes wasn't just about feeding, it was about cosmic collisions echoing through space-time. The early universe provided the perfect environment for both feeding and merging. Gas was dense, galaxies were close, and gravitational wells were deep. Black holes didn't need to search for fuel, they were immersed in it. Streams of primordial gas flowed along the filaments of the cosmic web, funneled straight into young galaxies where seeds lay waiting. These cold gas inflows could sustain black holes at extreme accretion rates for long periods. Unlike today, where galaxies are isolated and starved of fresh material, the early cosmos offered a constant supply line. This cosmic buffet may have been the key to unlocking explosive growth. With abundant fuel and frequent mergers, even modest seeds could transform into billion solar mass giants, just in time to light up the universe as quasars. But even with these mechanisms, something still feels extraordinary. To produce so many massive black holes so quickly, these processes must have been not just possible but common. That means the early universe may have been far more efficient at making black holes than we once imagined. Star clusters may have formed in runaway bursts. Gas inflows may have persisted longer than expected. Mergers may have happened at breathtaking frequency. What today would be considered rare, even exotic, might have been the normal state of the cosmos back then. If this is true, then these black holes didn't just appear early. They were part of the natural rhythm of the young universe, shaping it as much as it shaped them. The impact of these early giants reached far beyond their immediate surroundings. As they fed and merged, they released powerful jets and intense radiation that pierced through the fog of the early cosmos. This energy didn't simply vanish, it transformed the universe. These black holes heated and ionized the gas around them, helping to clear away the cosmic mist left after the Big Bang. They turned dark regions into glowing pockets of light, pushing the universe toward a new era. In this way, the first black holes were more than passive objects. They were engines of cosmic change, shaping their environment on a scale rivaling galaxies themselves. Their rise and the rise of structure in the universe were deeply intertwined. This era is known as cosmic reionization, the moment when light from the first stars, galaxies, and black holes reionized the hydrogen fog filling the universe. For a long time, scientists believed stars were the main drivers of this transformation. But evidence increasingly suggests black holes may have played a far larger role than expected. Their radiation is harder, more penetrating, capable of carving ionized bubbles that spread quickly through the intergalactic medium. A relatively small number of actively feeding black holes could have accelerated reionization dramatically. If this is correct, then the first black holes didn't just grow within the universe. They helped shape the very conditions that allowed it to become transparent and visible. This creates a powerful feedback loop. As black holes grow, they emit energy that clears gas from their surroundings, altering how galaxies evolve. In some cases, this may choke off further growth by pushing fuel away, but in the chaotic early universe, it may have done the opposite, opening new channels for fresh gas to flow in along the filaments of the cosmic web. This positive feedback could create a runaway effect. The more a black hole fed, the more it shaped its environment to feed even more. Instead of being isolated engines, these early giants may have worked in concert with their galaxies, accelerating their mutual growth. This synergy may be why early quasars appeared so suddenly, not as rare outliers, but as products of a cosmic system tuned for rapid growth. If black holes truly helped reionize the universe and shape its structure, then they weren't just passengers in cosmic history, they were architects. Their rise marks a turning point, the universe transitioning from darkness to light, from diffuse gas to structured galaxies. Their radiation and gravitational pull likely influenced where stars formed, how galaxies clustered, and how matter flowed along large-scale filaments. What we call the cosmic web may in part have been sculpted by their presence. This also means that understanding the first black holes isn't just about understanding quasars, it's about uncovering the engine behind the transformation of the entire universe, a force that shaped everything that followed. The fingerprints of this transformation are still written across the sky today. Astronomers can see them not in visible light, but in the faint background glow left behind by ancient hydrogen, a subtle signal from the epoch of reionization. The timing and strength of this signal carry clues about how powerful the first black holes really were. If they grew and fed as rapidly as current observations suggest, their influence should be detectable in the structure of the intergalactic medium itself. In other words, by reading the sky carefully, we can reconstruct their rise. And as technology advances, those faint whispers from cosmic dawn are slowly becoming clear voices. The James Webb Space Telescope has already pushed our view deeper into the early universe than ever before, revealing young galaxies that existed just a few 100 million years after the Big Bang. Among them, astronomers are finding hints of unusually bright, compact sources that may signal the presence of growing black holes. These are not the massive quasars we detect from billions of light years away. They are smaller, quieter seeds in the making. Observing them gives us a rare glimpse of black holes not in their prime, but in their infancy. Every data point helps refine the story, bringing us closer to understanding how the universe managed to create such monsters so quickly. Future observatories promise to push even deeper. Missions like Laser Interferometer, Space Antenna will listen for gravitational waves from merging black holes in the early universe, while next-generation telescopes will hunt for faint signals from the smallest seeds. By combining these tools, scientists can reconstruct how black holes grew from invisible whispers to cosmic engines. This is more than an astronomical quest. These observations may reveal which formation pathways dominated, how often mergers occurred, and how quickly accretion proceeded. They may even hint at whether primordial black holes truly existed. For the first time, we're approaching an era where these mysteries can be tested, not just imagined. These upcoming observations won't just refine our models, they'll rewrite them. By comparing light gravitational waves and the structure of the intergalactic medium, scientists can piece together when and how the first black holes formed. This multi-messenger approach will let us trace their evolution in ways that were impossible just a decade ago. It will also allow us to separate the fingerprints of different formation pathways. A universe dominated by stellar remnants would leave a different signal from one shaped by direct collapse or primordial origins. The more precisely we can measure these signatures, the closer we come to uncovering the true story of the first giants, and by extension the forces that shaped everything that followed. But even as technology advances, one truth remains. These black holes formed in a universe unlike anything we know today. It was hotter, denser, and far more dynamic. Star formation ignited in a flash, galaxies assembled at breakneck speed, and gas flowed through the cosmic web like rivers. In such a setting, growth that seems impossible now may have been almost inevitable then. What looks like a paradox to us may have been the natural pace of creation at cosmic dawn. The question is not only how the first black holes grew, but why the young universe was so efficient at feeding them. The answer to that question may reshape our understanding of structure formation itself. The first black holes are more than relics of a distant past. They are keys to understanding how the cosmos built itself. Their rapid rise hints that the universe may have been primed for black hole growth from the very beginning. These objects didn't just emerge alongside galaxies. In many cases, they may have led the way, anchoring the centers of young protogalaxies and driving their evolution through gravity and feedback. Instead of being passengers, they may have been the architects around which galaxies took shape. This flips the traditional view on its head. Perhaps galaxies didn't build black holes. Perhaps black holes helped build galaxies. This idea isn't just speculation, it's supported by what we see in the modern universe. Nearly every massive galaxy hosts a supermassive black hole at its center, and their masses are tightly correlated. This relationship hints at a co-evolution that may have begun at the very dawn of time. If black holes grew rapidly first, they could have acted as gravitational anchors, pulling in gas and stars, accelerating galaxy formation. Over billions of years, this bond between black holes and their host galaxies shaped the cosmic structures we observe today. In that sense, the rise of the first black holes may not have been a side effect of cosmic evolution. It may have started it. If this is true, then the search for the earliest black holes is also the search for the origin of galaxies themselves. Every early quasar we find isn't just a point of light from the past. It's a blueprint of how cosmic structure assembled. By studying their environments, we can learn how gas collapsed, how stars formed, and how gravity shaped the young universe. Their intense energy output likely regulated star formation, controlling how galaxies grew around them. These ancient black holes are not just astronomical objects, they are narrative threads woven into the very fabric of cosmic history, holding the timeline of galaxies and light together. This perspective transforms black holes from endpoints of stellar death into engines of creation. They may have set the pace of structure formation, dictated how galaxies matured, and ignited some of the first major feedback cycles in the cosmos. It also means their origins are tied not only to extreme physics, but to the architecture of the universe itself. To truly understand where we come from, we must understand how these cosmic anchors appeared so early, so massive, and so influential. Their story is in many ways the story of everything else that followed. As we peel back these layers of cosmic history, a larger picture emerges. The first black holes were not isolated accidents of physics. They were structural pillars of the young universe. Their gravity anchored galaxies. Their radiation reshaped space. Their mergers echoed through time. Every observation we make of them is like finding a fossil. Except these fossils are made of light and space-time itself. By studying them, we're not just learning how black holes formed, we're uncovering how the entire cosmic landscape was built. Their story began in darkness, but their influence still reaches us today, written across the stars, galaxies, and filaments of the universe. The deeper we explore the universe's first billion years, the more black holes reveal themselves not as silent observers, but as active architects. Their gravity sculpted galaxies, their energy reshaped the intergalactic medium, and their growth left imprints that we are only now learning to decode. This isn't just about understanding a few extraordinary objects. It's about uncovering the hidden framework beneath cosmic history, the forces that determined how light, matter, and structure emerged from darkness. And with every new observation, the timeline of black hole formation becomes sharper, more intricate, and more astonishing than anyone expected. What makes this story extraordinary is that it isn't over. These black holes may be ancient, but they continue to shape the cosmos today. Every galaxy with a supermassive black hole at its heart carries the legacy of those early seeds. Their formation wasn't a distant, isolated event. It was the opening act of a drama still unfolding. The gravitational ripples from their collisions still travel through space. Their influence can be seen in the way galaxies cluster, spin, and evolve. In this sense, the first black holes didn't just belong to the past. They built the universe we inhabit. To understand them is to understand our cosmic foundation. The rise of the first black holes is more than a scientific mystery. It's a turning point in cosmic history. It connects the moment the universe emerged from darkness to the structures we see today. It links the faint light of cosmic dawn to the vast web of galaxies stretching across space. Their story bridges two eras, one ruled by gas and gravity and another shaped by galaxies and stars. Without these early giants, the timeline of the universe would unfold very different. In many ways, they were the silent architects of everything that came after. The mystery of the first black holes began with a paradox: how they could exist so early. But now that paradox has become a map. By tracing their growth, their impact on reionization, their role in galaxy formation, and their fingerprints in gravitational waves, we are uncovering the structure of the young cosmos itself. Their story ties together nearly every major process in the first billion years. Star formation, mergers, radiation feedback, cosmic web flows, and the birth of galaxies. What once seemed like isolated beacons of light are now recognized as central players in the unfolding of the universe. And yet every answer reveals deeper questions, pulling us further toward the origin of it all. Somewhere beyond the distant quasars, beyond the galaxies, we can currently see lie the very first black holes, silent, invisible, and ancient. They are too faint for even our most powerful telescopes to detect directly, but their influence is everywhere, hidden in the structure of the cosmic web, in the ionization of the early universe, and in the seeds of the galaxies that followed. Finding them isn't just a matter of sharper eyes. It's about learning to read the universe's earliest signatures. These signals are subtle, but they're written into the fabric of space itself, waiting for us to uncover them. And when we finally do, the story of the universe's beginning may change forever. This is the next frontier of cosmology, not just seeing light but hearing the echoes of darkness. Gravitational waves, faint hydrogen signals, and indirect patterns will reveal what light alone cannot. Instruments like laser interferometer, space antenna, and future radio arrays will allow us to peer behind the veil of cosmic dawn. There, in that silent era, the first black holes were born. They left no light, only their gravitational fingerprints. And with every new generation of instruments, our ability to detect those fingerprints grows stronger. The hunt has already begun. Each step closer to detecting these earliest black holes isn't just about pushing technology. It's about pushing the limits of what we can know about the beginning of everything. Their formation holds clues about gravity matter and even the physics that shape the universe's first seconds. They are bridges between the quantum chaos of the early cosmos and the structured universe we see today. Studying them could reveal not just how galaxies formed, but whether there are deeper laws of nature we've yet to uncover. The first black holes may be ancient, but their echoes may rewrite our understanding of the cosmos itself. The coming decades will be a golden age for this hunt. Gravitational wave detectors, advanced radio telescopes, and deep infrared observatories will give us the power to trace the first black holes not through their light, but through their impact on the universe itself. Each new signal, a ripple in space-time, a faint radio whisper, a distorted glow from a young galaxy, will bring us closer to these invisible giants. The earliest black holes may have been born in silence, but their presence was anything but quiet. The cosmos still carries their fingerprints, waiting for us to uncover them piece by piece. The hunt for the first black holes is not just a search for ancient objects, it's a search for the moment the universe changed. Their birth marked the beginning of a new cosmic era. Galaxies assembling around dark cores, light piercing the fog and structure, taking shape on the largest scales. The clues are all around us in gravitational waves, faint radiation, and the architecture of the cosmic web itself. Each discovery tightens the timeline, refines the models, and brings us closer to the dark origins of these giants. And somewhere ahead, the universe's oldest black holes are still waiting silent but not lost. When we finally detect these earliest black holes directly, it will be more than a scientific milestone. It will be like turning the first page of the universe's unwritten history. For decades, we've known them only through their echoes, their distant light, and the scars they left on space-time. Soon, we may be able to see their birth not as distant myths, but as real, measurable events. Their discovery will not close a chapter. It will open one. It will reveal how darkness itself shaped the universe, and how the first cosmic giants carved the path for everything that followed. And when we arrive there, the story of the universe will begin not with light, but with shadow. To push beyond what we know, astronomers are designing precision tests to catch the earliest black holes in the act of forming. One of the most promising tools is laser interferometer space antenna, which will be sensitive to low-frequency gravitational waves produced when massive black holes merge at high redshifts. Detecting such a signal would be like listening to the heartbeat of the early universe. It would reveal not only how massive these black holes were, but how often they collided, giving us direct insight into their growth channels. Unlike light, gravitational waves carry information untouched by dust or time-perfect messengers from cosmic dawn. Alongside gravitational wave astronomy, the James Webb Space Telescope will continue to probe the faintest galaxies and quasars at extreme redshifts. Its infrared sensitivity allows astronomers to detect the earliest accretion disks, the glowing regions around young black holes as they feed. By measuring their luminosity and spectral signatures, scientists can estimate black hole masses and growth rates with unprecedented precision. If Webb detects black holes already massive just a few 100 million years after the Big Bang, it would strongly favor direct collapse or primordial scenarios. Every faint, distant light source it captures is potentially a seed black hole in its first breaths of cosmic life. Radio astronomy is another powerful key. Instruments like the upcoming Square Kilometre Array will map the faint 21 centimetre hydrogen line, revealing how early black holes influence their surroundings. As these objects heated and ionized nearby gas, they left measurable signatures in this background signal. By studying subtle fluctuations in the 21 centimetre spectrum, astronomers can reconstruct where and when black holes formed, even if they are too faint to observe directly. This allows us to probe their environment as well as their existence. It's like seeing the shadow of a giant before ever glimpsing its face. Combining gravitational wave data, infrared observations, and 21 centimetre mapping creates a multi-messenger picture of early black holes. Each method reveals a different aspect: mergers, accretion rates, environmental influence. Together, they allow scientists to test formation models rigorously. For example, if mergers dominate, gravitational waves will be abundant at high redshift. If direct collapse seeds are common, infrared signatures of massive early accretion disks will appear. Primordial black holes would leave a subtly different imprint detectable indirectly through the distribution of matter and early galaxy formation patterns. This integrated approach is essential to unraveling one of the deepest mysteries of cosmic dawn. All of these observations aim to answer a single fundamental question: how did the first black holes grow so quickly? Were they born massive, or did they feed and merge in extreme conditions? Did primordial physics play a role we've yet to uncover? By combining multiple observational channels and theoretical models, astronomers are beginning to constrain the possibilities. Each new quasar, each gravitational wave detection, each faint infrared signal adds another piece to the puzzle. Ultimately, solving this mystery will reveal not just the origin of black holes, but the processes that shape the universe's earlier structures, the foundations of galaxies, stars, and light itself. The study of the first black holes also informs our understanding of galaxy formation. Massive early black holes likely influenced the dynamics of surrounding gas, regulating star formation through feedback mechanisms. Their energy output could heat or expel gas, shaping the structure and evolution of young galaxies. This relationship may explain why supermassive black holes and their host galaxies display tight correlations in mass and activity today. By examining the earliest examples, scientists hope to trace the co-evolution of black holes and galaxies back to cosmic dawn. In this sense, the first black holes are both products and architects of the universe's formative years. Feedback from the first black holes was not uniform. Some galaxies experienced intense radiation and outflows that suppressed star formation locally, while others may have funneled gas efficiently toward the black hole, accelerating growth. Simulations suggest that these variations helped create the diversity of galaxy types observed today. Elliptical galaxies, spiral galaxies, and massive clusters may all carry imprints of early black hole activity. By connecting black hole feedback to galaxy morphology, astronomers are beginning to see the first black holes not only as relics, but as dynamic agents that shape the architecture of the universe itself. Mergers between early black holes also played a key role. In a universe where galaxies were closer together, collisions were frequent. When two black holes merged, they combined, their mass grew faster, and sent gravitational waves rippling across space-time. These mergers could create some of the earliest supermassive black holes, explaining their surprising masses at high redshift. The signals of these events are now targets for next-generation detectors like laser interferometer space antenna. By detecting these ripples, astronomers can reconstruct a timeline of early mergers, providing insight into how black holes coalesced and shaped the young universe. Cold gas inflows along the cosmic web provided another crucial channel for growth. Streams of pristine hydrogen and helium could funnel directly into young galaxies, feeding black holes at high rates without interruption. These cold flows create environments where black holes can sustain near-constant accretion, bypassing the limitations of intermittent stellar feeding. Combined with mergers and super Eddington accretion, cold gas inflows make rapid growth plausible, even in the universe's first few 100 million years. This mechanism links large-scale structure directly to black hole evolution, showing how the universe's scaffolding supported its earliest monsters. Primordial black holes remain the most speculative pathway. If density fluctuations in the immediate aftermath of the Big Bang were extreme enough, regions of space could have collapsed directly into black holes seconds after the universe began. While direct evidence is lacking, their existence would explain how some supermassive black holes appeared too early for stellar or direct collapse seeds to account for. Primordial black holes could have served as universal seeds silently waiting in the cosmic darkness, shaping the formation of galaxies and the earliest quasars before stars had even formed. The combination of these pathways, stellar remnants, direct collapse, primordial formation suggests a universe rich with black hole seeds. Some were small and grew through accretion, others were massive from birth, and a few may even predate galaxies entirely. This diversity provides a natural explanation for the variety of quasars and supermassive black holes observed at high redshift. It also implies that the early universe was an environment where extreme physics was the norm rather than the exception. Understanding the balance between these mechanisms remains one of the most compelling challenges in modern cosmology. Observations and simulations now work hand in hand. High-resolution cosmological simulations track how gas, dark matter and black holes interact, predicting how early seeds might grow under realistic conditions. Comparing these predictions to observations from James Webb Space Telescope allows astronomers to rule out implausible scenarios and refine models. Each newly discovered high redshift quasar provides a data point to validate or challenge theories of black hole formation. This iterative process is crucial for understanding how the first black holes shaped the cosmic landscape we observe today. The early universe's density and temperature played a critical role in black hole growth. Dense gas clouds funneled matter efficiently into potential wells, while higher background temperatures influenced cooling rates and star formation. These environmental factors combined with mergers and accretion could explain how black holes reached extraordinary masses so quickly. Understanding these conditions helps astronomers identify where to look for the youngest and most massive seeds. By linking cosmic conditions to black hole evolution, we begin to see a coherent picture of how the universe built its first gravitational titans. Studying the environments of early black holes also sheds light on the first galaxies. Gas inflows, radiation feedback and mergers all influence both black hole growth and star formation within the same regions. This interplay created a feedback loop. As black holes grew, they shaped galaxy evolution. As galaxies formed, they provided fuel for further growth. Observing these early systems allows scientists to connect the dots between black hole formation and the assembly of the first luminous structures in the cosmos. In essence, the rise of the first black holes is inseparable from the rise of galaxies themselves. The earliest black holes also inform our understanding of reionization. Their high-energy radiation contributed to ionizing hydrogen across the intergalactic medium, complementing the radiation from the first stars. By estimating the number, mass and growth rate of these black holes, astronomers can assess how much they accelerated the universe's transition from opaque to transparent. Their contribution may have been significant, reshaping the timeline of cosmic dawn. Thus, the first black holes were not only architects of galaxies, but also agents that cleared the cosmic fog, allowing light to travel freely for the first time. Looking forward, next-generation observatories will provide unprecedented insights. Telescopes like the Extremely Large Telescope (ELT) and space-based infrared instruments will detect fainter and more distant quasars, revealing black holes closer to their formation epoch. Simultaneously, gravitational wave detectors will capture mergers of early black holes, offering a direct view of their growth via collisions. Together, these tools promise to uncover the full life cycle of the universe's first giants, allowing astronomers to test each formation pathway, stellar remnants, direct collapse and primordial origins with real data rather than theory alone. Every discovery of a high redshift black hole adds to a growing map of the early universe. By combining observations of quasars, accretion disks, mergers and environmental effects, scientists can reconstruct a timeline of how the first black holes formed and grew. This multi-messenger approach allows for cross-validation. Gravitational waves confirm mergers, infrared light reveals accretion, and 21-centimeter observations show the impact on surrounding hydrogen. Together, these methods provide a comprehensive view of the universe's first monsters, linking black hole formation to galaxy evolution and cosmic reionization. The data we collect today will inform simulations that attempt to recreate the early universe. By inputting observed properties of black holes, gas inflows, and galaxy environments, scientists can test whether their growth can be explained by known physics or if new mechanisms are required. These simulations also help predict where future observations should focus, guiding the search for the smallest seeds or the most massive early black holes. In this way, observation and theory work hand in hand, gradually revealing the processes that allowed the first black holes to rise so rapidly in the young cosmos. As simulations improve, they reveal subtle interactions that might have accelerated early black hole growth. For instance, dense gas flows along cosmic filaments could funnel material efficiently, while nearby star formation could generate radiation that regulates accretion rates. Mergers of black holes within close protogalactic groups may have further boosted mass growth. Each factor compounds the others, creating conditions in which black holes could reach extraordinary sizes much faster than previously predicted. Understanding these complex dynamics is essential to explaining how the universe produced its first supermassive black holes so quickly. Observations also suggest that early black holes were not solitary. Many resided in dense clusters of proto-galaxies where frequent interactions and mergers were inevitable. These crowded environments amplified growth opportunities, providing both fuel and collision partners for black holes. Such clusters could explain the apparent overabundance of massive quasars at high redshift. By studying the distribution and frequency of these objects, astronomers can estimate the typical environments where early black holes thrived. This paints a picture of the early universe as a bustling network where black holes formed, grew, and influenced everything around them in rapid succession. Feedback from early black holes had profound consequences for their host galaxies. Radiation and outflows could regulate star formation, preventing gas from collapsing too quickly, while shaping the density and structure of the surrounding medium. In turn, these galaxies determined how much material the black holes could accrete. This mutual influence established a co-evolutionary relationship linking the growth of black holes to the assembly of galaxies. Studying this interplay at high redshift helps explain the tight correlations observed between supermassive black holes and their galaxies in the modern universe. By examining the light from distant quasars, astronomers can infer the mass spin and accretion rate of early black holes. Spectroscopy reveals the composition and velocity of surrounding gas, indicating how rapidly these objects are feeding. Combined with models of galaxy formation, this information helps constrain which formation pathways were likely. For example, extremely massive seeds observed early may favor direct collapse or primordial scenarios over stellar remnants. Each new observation sharpens the picture of how black holes became the cosmic titans we see even in the first billion years. The story of the first black holes is far from over. They are more than relics. They are foundations of the universe's structure. By tracing their origins, growth and influence, we uncover the processes that shaped galaxies, regulated star formation, and even contributed to cosmic reionization. Future observations promise to reveal whether these giants were born massive, grew through extraordinary feeding, or emerged from primordial fluctuations. Each answer will not only explain the past, but also point toward new mysteries, hinting at forces and events that remain hidden in the dark. The first black holes mark the beginning of a larger cosmic story, one that is only just beginning to unfold,